In this session, I'll explain about UDP protocol. This is a play.pcap. This is a file I have downloaded from help to sample captures, and here I have downloaded. So this is a simple file that has a SIP protocol and RTP. SIP is a connectionless protocol in a transport layer above the IP layer. Sorry, not SIP, UDP. UDP is the transport protocol, which is in the layer transport layer or a layer 4 in the OSI model. Right, first layer is physical, and second layer is data link, third layer is network layer, and fourth one is a transport layer. So UDP is UDP and TCP are the transport layer protocols or transport layer, and SIP is a session initiation protocol, which is used in telephony or VoIP. And so why we have chosen this to discuss the UDP, because SIP is a protocol on top of UDP. SIP, trivial file transfer protocol, and the DNS uses the UDP UDP for the transport, and HTTP and FTP other protocols uses TCP for the transport. Most of the protocols. So when UDP is used, UDP is a connectionless protocol. UDP is used whenever we need whenever we want to transfer the time-sensitive data, time-sensitive information, because UDP doesn't have any overhead of connection establishment. So we can go to File, Open, and there we can choose the file. Or I have already opened, so it is displayed here in a recent open file. So double click to open. And we have learned that here is the intelligence scroll bar, and we have the packet list, packet details, and packet. Those are the panels here. And to discuss the UDP, I can select any SIP protocol. So first thing you can do is go to Analyze Statistics, and there select the protocol hierarchy. There you can see how protocols are encapsulated. So you can see here in a UDP what protocols in this file, capture files, what protocols are using UDP transport, or what application layer protocols are encapsulated into UDP. You can see here session initiation protocol, RTP protocol, real-time transport protocol, RTCP protocol, NetBIOS, and the dynamic host configuration protocol, which is a DHCP, domain name system, which is a DNS. All of these protocols uses the UDP, and there is a FTP, which uses the TCP for the transport. And so all of these protocols are time sensitive to take the real-time data. So we want to know, we want no delay in we want no latency or lost in the connection establishment, so that there is no three-way handshake in a UDP that we will discuss. Three-way handshake in a that is required to establish a connection or to tear down a connection in a TCP. What is the packet structure of a UDP? So if you take any of the packet here, so DNS uses the UDP transport. You can see here. So DNS protocol, which is encapsulated into UDP, user datagram. You can see that, and it is encapsulated. These both things are encapsulated into IP, and you have the frame header. Here it is a frame, so which represents the whole data. Okay, now go to this frame header. Contains again this source address, destination address, right? And then you have the protocol type, is IPv4. This is a data link layer frame. And go to the UDP. That is what we are discussing. You can see here UDP is very simple, lightweight protocol. It's unlike the IPv4 or TCP. UDP packet structure is not that complex. It has only 4 fields. There is a source port, destination port, length, and checksum. So what is source port? We have learned that TCP, every layer has a different addresses. You can see here how many layers. We don't have any address in the application layer. Usually application layers, this is taken care of that application layer protocol. And what is the address in the UDP, which is a port number? And what kind of address is used in a PD of IP internet protocol internet layer? That is a IP address, which is also referred as logical address. And in a Ethernet layer or data link layer, the addresses that we use is a MAC address or a physical address. So here, if you select this UDP, you can go here. Those addresses are used. Addresses, these port numbers are like a windows to the applications. Window, doorways to the application. These port numbers are used to identify. They are used for the process-to-process communication, where each process that opens the socket for the communication binds itself to the random port. There are three types of port numbers that are well-known ports, or here if we go here, we can see there are three types of these total 65K ports are used. The ports are there because the port address or a port number uses the 16-bit to represent a number. So that is what you can see here in a UDP packet. So the source port uses the 16-bit out of or 2 bytes, and destination ports uses the 2 bytes. So 2 bytes are required to represent the port number, which means that total it can represent 65K, 65,560 up to 565,000, up from 0 to 65,565 it can represent. So out of the 65,656 ports, what are how these are categorized? These are categorized into three. These are categorized into three ranges that are system ports, that are from 0 to 1023, and user ports, these are 1024 to 49,151, and there are dynamic ports or private ports. These are from 49,150 to 65,535. So these are different ranges, and these are also known as system ports, are also known as well-known ports. So that you can see here. So these system ports till 1024, these are all reserved for a one or other use. So these are all called well-known ports, system ports. See, okay. So however, may unofficial use both well-known ports and registered ports in practice. So these and also one more thing, in a Linux or other systems, if you want to use any port that is below the 1024,000 or 1024, you should need admin privileges, or they won't allow you to bind. Anyway, so this is the registry. This is where we have seen these port numbers, and some other. From 1024, there are some ports that are registered. For suppose you can see for the specific purpose. OpenVPN uses the 1194 port. So that way, we have some ports that are registered for a specific purpose, and that we have seen here. 49,151. This is what we have seen in our port numbers. You can see 49,151. These are referred as user ports or registered ports. And from 49,152 to 65,535, we refer them as a dynamic ports or private ports or are also sometimes referred as ephemeral ports. So these are used by applications when these are mostly used by the clients when they want to make a network connection to the server. So some applications uses the port from dynamic support from the registered any port, random port from registered port to uh, ephemeral ports as well. But this is a standard way that applications use, applications bind to, or applications choose the random port from. And so here we can see those are the port numbers. So these are used. What this port number is like a window or doorway to identify the process. The process is when you run an application that becomes a process in the memory. So to identify the process. So likewise we use the inner LAN, we use the MAC address to identify the system or the network device. Likewise we use the IP address to identify the system regardless of the physical medium in which. Like that way we use the port number to identify the process. So any process that opens the socket when for the network connection binds itself to the any of these ports. If it is a server, the mostly that uses any of the port from registered port or registered port pool or from the well-known ports. And so any client application such as browser, anything, or a DNS client that uses mostly the port from the ephemeral, any port from the ephemeral or private ports or dynamic ports. You can see here that we have registered port. What are some registered ports we have? Let's say some of the well-known applications that you use are SMTP, which is used for a mail transfer. That is a 25. And for suppose there is a DNS uses the 53. So that we can see here those ports here as well. You see FTP uses the 21 port, UDP. So which protocols are using UDP or TCP? We can also see them here. Anyway, you can see here so what is another one? DNS. DNS uses, yeah, DNS uses the 53 protocol. First, sorry, not 53 protocol, 53 port number. DNS protocol uses the port number 53. Okay. So, and so let's go here. We can see if I go and dig deep into the DNS here, it is from the client to the server. So tell me which port it is using here in a source port. What is the destination port, which is a 53? So DNS, domain name system, DNS server uses the port number 53. Port number 53 for a on a server. But a client uses what? Any port from any random port. So here it is 27,100. Sorry, 22,730. See, which is not in the, which is basically the a port in the registered port, but that is not a. See, this is what it is. These registered ports are from 1024 to 49,151. So other applications that we have limited 1,000 ports, but most of them are system ports are well-known ports from one application or other application. But thing is, when it comes to registered ports, other applications can register like a SOX, POSI, and so that they are kind of unofficial standard ports. But some of ports are not reserved and not registered, so they can also be used. They are also selected by the client applications to bind themselves when socket is open. For suppose you can see 2713 is not a in the registered port, that is not that is used that way. So So client applications uses a port from basically 1024 to 64,535. So here the DNS client is identified in itself by the port number 2713, and DNS server is identifying itself. DNS server process identifying itself in operating system to the using port number 53. So when for suppose when the packet is received by the destination, when a packet is received by the destination computer, which is a DNS server, that frame network interface controller strips off the frame header and gives it to the operating system internet protocol module, and that will strip off the IP layer, IP header, and identifies the port number. That has a transport layer, which is a 53. So it identifies the process that is bound to the socket on that port, which is 53. That would be the DNS server. So it gives that data by stripping off the UDP, the UDP header, which is that application receives the DNS. Of course, applications require if they want, they can actually read the whole the packet. So, but this is a process. So you can see here that when it comes to as we see here, the source port, destination port, and length, which is a packet length, and checksum. Checksum is not mandatory in IPv4, but according to the protocol IPv6, the UDP checksum is mandatory. And this is used, checksum is used to identify the packets that are corrupted so during the transit. So see this packet structure in a Wireshark. Here, if you go to UDP, select this UDP protocol, and you can see here what is the length of the packet, UDP packet header, which is 8 bytes, fixed 8 bytes. So you can see here 8 bytes. How many? 1, 2, 3, 4. 4 twos are 8. Total 8 bytes. So out of 8 bytes, the 2 bytes are source port, and second 2 bytes are destination port, and third 2 bytes are for length, and last remaining 2 bytes are for checksum. You can see here how many bytes. If I highlight in a bytes packet bytes panel, you can see that the data is highlighted. So you can see this one is the port address. You can see when I select this one, you can see the corresponding data that is presented in pretty manner. This is a source port, and next 2 bytes are destination port. You can see the 53, and the next 2 bytes are length 52, and remaining next 2 bytes are last 2 bytes are for the checksum. So here you can see here, so what is the 52? 52 is used to count the whole packet length, which means out of 52, what we have, so payload, what is the UDP payload length? 44. So it is carrying a data of size 44 bytes. But this length field in the UDP packet counts the length, total length, which includes the board header and body. So you can see that's length as it is interpreted by the Wireshark, it is showing the payload is a 44. And what is the fixed length of the, so what is the length of the packet header in UDP, which is 8. 44 plus 8, 52. You can see the total length. And as you can see this, what this UDP payload is carrying, which is the data from the application layer, which is the DNS protocol, encapsulated into this UDP. You can see here, when I select, you can see when I select anything, that information displayed in a status bar here. You can see the 44 bytes payload UDP, and what you see here, what checksum is used to identify any corruption in the packet, any kind of, yes, if a packet is corrupted or not, that can be identified using checksum. Checksum is calculated for a whole packet, which is used to verify the integrity of the packet. So for suppose checksum is checksum is calculated. Checksum is calculated for the whole packet, which is like a what do you say, that is like a checksum is like a which is a 16 bits, which is like a stamp. What do you say? Okay, so which is calculated for the whole packet, and that would be if when a packet is sent by the client, checksum would be calculated and inserted into this field. When it is received by the server or other end, so that will calculate the checksum for the whole packet, and that will compare the checksum calculated by the receiving end with the field that is placed, that is with the checksum that is inside this field, which is a UDP header. So if both are same, which means that packet is not corrupted. If for suppose the calculated receiving and calculated checksum is different from the checksum in the UDP packet, which means that packet is corrupted. There might be some bits might have been lost during the transit, or some bits might have been flipped due to the some interference or whatever. So this is used to verify, this checksum is used to verify the integrity whether the packet is corrupted or modified or not, is verified by the checksum. Okay, do you understand? Okay, so let me tell you that how checksum works with there are some protocols used, some checksum protocols are also used, that are some hashes are used in real world for the checksum. Even you can see here, you can see on different sites MD5 checksum, SHA-256 checksum when you download the file, because when you download the file, after downloading you can calculate the checksum. So when to confirm whether you downloaded that whole file properly or not, by calculating checksum and verifying the checksum with the checksum that is listed on the website. So here that how checksum is calculated, it uses a different way in a UDP. Okay, the first suppose let me tell you how checksum works. Just a simple, using simple example. Okay, here I'm using Python. See, this is I'm giving you just to give you. So in some applications, in application layer protocol, we uses hashes, MD5, SHA-256, like that. But here in how checksum is calculated in a UDP or in a TCP, that is different. So we will learn about that in coming sessions. But here I'm telling you, but the whole point of using checksum is same everywhere. Or suppose I have data. Let's say put data, hello world, welcome to Wireshark. Okay, this data I sent you, imagine, just assume I sent this data to you, but you want to verify whether this is the same that I have sent or someone modified in the middle. Okay, so this packet can be intentionally modified by the hacker or man in the middle attack, or these packets or bits might get corrupted because of some interference involved during the transit. So let me calculate hashlib dot. So this is a checksum. Can you see here? For suppose, okay. So this is a checksum calculated. So this is the MD5 hash that is used as a checksum in many cases, many other cases. So here you can see that hash. For suppose, let me change the data. Okay, let me use the same data, but let's change hello world. Instead of hello world, let me use the question mark, and I will use the same for the remaining data. Okay, remaining message. So here I'm using, instead of data, I've been using data2 variable, which means the second one. So tell me, are these two same here? Are these two checksums same? No. So for suppose you sent me this message, and also you will give me this checksum as well. After I receive message, for suppose because of interference or someone changed the exclamatory mark with the question mark. So I need to make sure this is, I'm giving you this with a small example, but this might be a lot of GBs of content or like that. So here in this case, I can calculate the checksum myself, and I can verify this checksum with the checksum that you have given. So if both are not same, so the data you have sent and the data I have received, both are different, because both are different. The reason could be either they are corrupted or modified by the someone in the middle intentionally. So now check here, if I calculate hashlib.sha1 of, if I calculate the data, which is the first one, I'll get the name no matter, okay, see, which is, it is same as this one, okay. So likewise this checksum is used. So here it is unverified in a Wireshark. Why? Because verified, you can actually go to Wireshark, and their protocol options are available there. You can see here, show UDP summary, and the calculates there. You can validate the UDP checksum possible. You see, so but that is, you see, it says correct here, which means that it validated the checksum. That is, so what Wireshark did, it calculated the checksum for the whole packet, which means this whatever is whole packet means this UDP header and data, and comparing that with the checksum here. See, calculated checksum, you can see when you open this one, calculated checksum is a DD59, and which is same as the the checksum that is there in the UDP checksum field, if the both are correct. But that is not always required, but because calculating this checksum sometimes may put some overhead on a processor, so you may optionally check this one, validate or uncheck that. So what is the summary here? When the checksum field here, so likewise here you can see checksum. Let me do that again, validate the checksum. So this is calculated by, let's assume Wireshark is the receiving party. Let's say assume this is a receiving party, the server. It calculates the checksum here, and also it compares that calculated checksum of the packet with the checksum that is provided in the field. If both are same, that will assume that this packet is correct. That will consider packet is correct. If both are different, likewise we have seen in this example. So packet is modified or corrupted, so that packet will be usually dropped by the application, receiving and application, or the module, UDP module, or the network interface controller are receiving that corresponding service in a OS or receiving computer or system. But what if and they are dropped and there is no acknowledgement in the UDP? That is the reason UDP, of course, UDP is fast and best in time sensitive, but there is a downside for UDP. It is not reliable as a TCP because there is no error correction, flow control, congestion control mechanisms in the UDP. And so sending the application that sends these UDP packets assumes that those packets will be delivered to the receiving computer. Those packets, it assumes that those packets are received by the receiving computer. So sometimes here this error mechanism is handled by the upper layer protocols. So where if that is just in case, if what happens if this packet is corrupted, that will be dropped, and sometimes if the sending party may resend the request again if it doesn't receive any of the reply. Okay, this is as simple as that one. So there are 4 fields, and you can see here that if you go to payload, which is same as the payload of the whole whole length of the DNS packet. Okay, DNS data, which includes which is, you can see here 44 bytes here in status bar, which is same as the UDP payload. And you can see on right side also, you can see some other options that are how many packets are there, and how many are displayed and profile. That way this status bar is also quite helpful. And if there are any issues or warnings, you can go to this expert information. Suppose if you see any of the issues in UDP or other protocols, we can go to expert information by clicking on this one. And this is about simple. So click on this bottom left corner, click on this color circle, and there you will see the expert information. This is a consolidated summarized information that Wireshark finds. So if there is and these are actually different levels here, warning, and there's a severity levels there are, but it doesn't has any errors, but it has any warning notes and chart. You don't have to worry about note and chart, but you have to worry if there's a warning, there is an error. Okay, and when network administrators use this information provided by the Wireshark to troubleshoot any of the issues in the network, such as malware analysis or intrusion detection system, threat analysis, those can be done here, but that is the discussion for the other day. I hope you understand the UDP protocol.